Welcome to topic 12, which is the final topic of uniform circular motion. And that after this, we will be left with just one major topic in Unit 1. So far in uniform circular motion, we've talked about centripetal acceleration and tangential velocity and that stuff. We've also talked about centripetal force. We've talked about how that works in a horizontal circle. We've talked about how it all works in a vertical circle. So that's in the previous 3 units to this one, 9, 10, and 11. What we're going to look at in this lesson is banked turns. Because when you have a horizontal turn, like a horizontal circle, a car going around a curve, for example, it normally relies on friction to keep it on the road. But when it comes to things like a racetrack, and if you ever watch any NASCAR races, you'll see that the turns are always banked at an angle. And the reason for that is it helps the cars stay on the road. It prevents them from sliding because it introduces another force besides friction. So let's take a look at how that works. Okay, so the diagram that you see there at the right shows an end view of a vehicle going around a banked turn. A banked turn. So we've got a number of different forces involved here. Now, the important thing to note is this car is not sliding down the ramp. Okay? It's not going down this way. It's not coming down like this. It's going into the page, if you like. It's moving in a circle around that turn. Not sliding up or down. We want it to stay just where it is. So what we're going to do is we're going to look at this with no friction. So the most important force here is the force of gravity. This brown vector right here. Okay? That brown vector is a very, very important force. It's a vertical force, but we're moving in a horizontal circle. But it's a horizontal circle on a banked surface, on an incline. So that makes it a little bit different. So the most important force of all, then, is the normal force, because that's the force pushing out against the car. That's what keeps it from sliding, in other words. But if you look at the normal force carefully, you'll see that the normal force is actually at an angle. If we're going to talk about a horizontal circle, we're more interested in this orange vector right here, which is the x component. Now, because of where our angle is, you notice our angle is not here measured from the horizontal. It's actually up here measured from the vertical. So that's why we're using sine here instead of cosine to find the normal force. Now, what we're going through here, you're not likely going to be asked to reproduce this. In fact, I'd be shocked if you were. But it's always nice to know where these equations come from. So there's where that comes from right here. Fn sine theta is the horizontal component of our normal force. That is what keeps our car moving in a circle if there's no friction. Okay, so we're going to leave friction out of this completely. And you see some other forces there as well. We'll get back to those in just a second. So let's take a look at a truck going around a 30-degree bank turn. Now, the bank of the angle right now is not really important, but remember the forces are Fg and Fn. Those are the only 2 actual forces there. Okay, our centripetal force is caused by this guy right here. In other words, the horizontal component of the normal force. Because see, look, gravity, because it's straight down, doesn't have a horizontal component. The normal force does because it's acting perpendicular to the surface, which means it's going to be at an angle to the horizontal. So that's why we do this. So we've got Fc equals Fn sine theta, sorry. Fc equals Fn sine theta. That's the centripetal force. So in other words, mv squared over r equals Fn sine theta. That's one equation. That's the horizontal equation, we'll call it. We'll call that the horizontal equation. But there's also an equation for vertical forces. Just look. If you look at it, there's actually 2 vertical forces as well. Right? There's a vertical component to our normal force, and we also have our force of gravity. So if we make the two of those equal, we've got mg equals Fn cosine theta. And I'm going to call those equation 1 and equation 2. Now if I divide those two equations, look what happens. If I take equation 1 over equation 2, equation 1 over equation 2, equation 1 divided by equation 2, look what happens. The masses would cancel. The FNs would cancel. That would leave you with V squared over GR, or RG, and it would leave you with sine over cosine. Okay, sine over cosine. That's why tangent is written there. Because if you think about your trig identities that you learned in mathematics, sine over cosine actually equals tan. So that way we only got one trig function there instead of two. We can do that little simplification. That equation right there, this equation right here, is the equation that applies to a bank turn with no friction. Bank turns with no friction, that's the equation. Now that's not the way it's written on the formula sheet though. It's written in a slightly different way. It's written in terms of R. R equals. So I'm just going to turn the screen here. There's what it actually looks like on the formula sheet. Okay, so this one right here is actually on the data sheet, and it looks exactly like that on the data sheet. Now that can be rearranged to solve for V. You get V equals the square root of RG tan theta, or it can be written in terms of tan theta equals RG, or sorry, tan theta equals V squared over GR, or RG. There's a bunch of different ways you can write that. Now, the thing to remember is this. It only applies with no friction. That's for no friction. If there's friction, you can't do it. Okay? We don't do any examples of bank turns with friction in Physics 3204. You wouldn't know how to do it. You wouldn't be expected to know how to do it. So if there's no friction, that means that if the car goes faster, it's going to start to slide up the bank curve. It's going to start to slip up, which is what sometimes happens in these NASCAR races. The cars lose their traction and they'll start to slide up the track and crash into the wall. Or if it goes too slow, it would start to slide down the bank turn as long as the road is completely frictionless, which of course is not really going to happen, but the turns are banked to reduce the reliance on friction. But to simplify things, we just look at a frictionless surface, because that simplifies the calculation. Now you note that the mass of the vehicle is missing. What that means is a heavy truck and a light car would both behave exactly the same way on a bank turn. Because of the way things cancel out when we ignore friction, it wouldn't make any difference if the truck was heavy or light. Empty truck, fully loaded truck, makes no difference. They both behave in exactly the same way. And I mean exactly. Let's look at some examples. And I'm going to look at both. I'm going to show you a couple of multiple choice questions off of Old Publics. And I'm also going to show you a constructed response, or a long answer question off an Old Public. Now I will say this though, that bank turns are not a major topic. So it's not very likely you're even going to see it at all on part 2. Most often there is just one multiple choice, and that's it. That's the way it's covered on the public. Now, that being said, it could be different. I'm just telling you what's most likely to happen. So, most likely you're going to get a question similar to one of these. At what speed could a car safely negotiate a frictionless curve with that radius? Well, as soon as you see a banking angle, as soon as you see bank turn, you know that it's this equation. Okay? And the equation is, and it's straight off the formula sheet, the equation on the formula sheet is R equals V squared over G tan theta. Now obviously, because I'm asked to find the speed here, I need to rearrange that. So I cross multiply and I get V squared equals RG tan theta, which means V equals the square root of RG tan theta. So it's just a matter of plugging in those numbers. The R, the radius, is 115, the G, 9.80, and the angle, 35 degrees. And if you plug in those three numbers, you will get this answer, 28.09. And that, of course, rounds off to 3 sig figs, because if I look here, there's 3, and there's 3. 28.1 would be what it rounds up to. So there's the safe speed. Any faster than that, it would start to slide up the curve. Any slower than that, it would start to slide down the curve. So if you had a really icy road and it was banked at that angle, you could actually drive around that turn at 28 meters per second, which is around 90 kilometers per hour. Actually, it's more than 90 kilometers per hour. And you could do that safely if the road, even if the road was slippery, because it's banked. What banking angle would be required? So this time, it's the same formula. Okay, straight off the formula sheet. But this time they ask you for banking angle. So I would rearrange that equation like this. This time tan theta equals V squared over RG. That's the rearrangement of the formula. V squared over RG, or GR, okay, whichever way you want to write it, doesn't really matter. Now, the only thing you got to be careful with in these questions is make sure your speed is in meters per second. It is in this case. Make sure your radius is in meters. It is in this case. So you're good. Everything is good. So you plug in the numbers. So I've got 24.5 squared. My radius is 110.0. And my G is always 9.80. So plug all that in and you get 0.5568. Now that's not there obviously because that's tan of the angle. So in order to get my answer, I have to say theta equals second function tan of 0.5568. And do that calculation, you get this angle, 29.1 degrees. 29.1. Now, this last question, this was on an old public exam, and that's the reason that I showed you all that stuff about where the formula comes from for banked turns. Because if we hadn't gone through that, you wouldn't have known the answer to that question. So remember now, the centripetal force, because it's horizontal circles, we know we can eliminate the vertical components. We don't need any vertical components because it's a horizontal. Cars don't move vertically, they move horizontally. So it's the horizontal component of something, and it's the horizontal component of the normal force. Remember, weight, because weight is straight down, weight has no horizontal component. There is no horizontal component to weight because weight is force of gravity. So it doesn't have a horizontal component. It only has a vertical component. So obviously B can't be the right answer either. It has to be choice A. One more question left to show you. This one is the only question involving banked turns that's been on the public exams in the past 4 years. So it's rare. It's most often covered in a multiple choice question, like I said, or a selected response. So if we want to calculate the angle at which the road must be banked, we just did one like that, right? We just take our equation. Remember, our original equation was R equals V squared over G tan theta. That's the equation on the formula sheet. We rearrange it as tan theta equals V squared over R times G, which I just showed you a minute ago. And we plug our numbers in, and we get our answer, 16 degrees. And this time we do it to 2 sig figs because these numbers up here both had 2 sig figs. So there you have banked turns, which is a special case of uniform circular motion. It's still a horizontal circle, but it's a horizontal circle on an incline. So it's a special case. But that's the formula you always use. And like I said, most often will be there as a multiple choice question, not as a long answer. It's possible, but unlikely. So that concludes uniform circular motion. The next topic that we're going to be looking at is static equilibrium and torque. And we're going to do another 3 to 4 topics related to that. And that will finish off then Unit 1. So after the next day of classes, the next set of recordings, we will be finished with Unit 1 and we'll move on to Unit 2. So, as I always say, good luck with your review, good luck with your studying, good luck on your exam.